Welcome back to the channel. First of all, a quick apology for not posting frequently last week. I was caught up with some intense office work, but we are back, and in this episode we are going to do something very hands-on. We'll walk through our own implementation of byte pair encoding, the BPE. So this implementation, I would like to say, is intentionally very simple. We are not optimizing for speed, we are not optimizing for production. Our only goal is basically readability and understanding. So what we are building here is we'll focus on character level BPE. We'll allow only two character merges at a time, and later on we will compare the behavior with the GPT-2 tokenizer. To understand the code clearly, we'll use a single sentence like, let's say, I love mountains, right? So let's understand the code. So our first function, like the first step in constructing the BPE algorithm, is basically defining a frequency function like get pair frequency. So the job of this function is very simple. It counts how often adjacent pairs of characters appear. At the beginning, our sentence is split into characters like I love mountains is split into I space LOVE space and mountains. At this stage, there are no words, no subwords, just a flat sequence of symbols that you see here. Every character, including spaces, is treated exactly the same. This is intentional. BP does not assume anything about language structure. It only works with patterns and frequencies. That's it. Now, let's understand how does the counting of adjacent pairs occur. Now we slide a window of size 2 across the sequence, like here you can see, right? And count pairs like L and O are together, O and V are together, M and O, space and I. Every adjacent pair is counted. Once all counts are collected, we ask a single question like which pair appears the most. That will become our rule, right? The pair that becomes a candidate for merging. And this is extremely important. This is the only decision that BPE ever makes. There is no grammar, there is no meaning, frequency decides everything, right? Now let's understand the second function, which is merge pair. Once we know the most frequent pair, we move to the next function, which is basically merge pair. This function does exactly what its name is, right? If the most frequent pair is L plus O, then every occurrence of L and O in the sequence becomes LO, right? This merge creates a new token. We don't partially merge, we don't merge selectively, we replace basically all occurrences in one pass. That's it. So each merge adds exactly one new token to our vocabulary. This is how the vocabulary is constructed, right? You can see that. Now, how words emerge? Like as we repeat this process, you will observe that something interesting starts to happen, and that is what the train BP function does. Over time, we see progression like L plus O will become low, LO plus V will become LOV, LOV plus E will become love, and similarly, like M plus O will become MO, MO plus U will become MOU, and so on till mountains. Without basically ever knowing what a word is, our tokenizer, our own tokenizer that we are trying to construct, slowly discovers like words through repetition. This is one of the most beautiful aspects of BPE. Words are not defined, they basically emerge. Now let's look at like what we have actually trained. Remember, we are using a dataset that is on Hugging Face called Tiny Stories, right? And if you look at the structure of this dataset, let's just have a quick look at the structure here. Yeah, it's going to take some time here, right? And if you see here, you have got features, text, number of rows, validation, and number of rows. We are just taking the trained part. This is just for educational purpose and 1,000 sentences. And then we run our own train BP, right? The process that I was just defining. Let's look at the number of merges, right? The merges you can see here. We have extracted like the top 500 merges or the top 500 rules for tokenizing a sentence, and you can see here, right? Merges here. You can see that OW plus N are together, LO plus V are together, was and very are together, right? Basically, tokens which are occurring most importantly together. That's what we are defining. Now let's, as we have extracted the rules, let's look at our sentence. Like we apply BPE on I love mountains, and you can see that I, then space LOVEMOUN. It's got like long. Like let's measure the length here. It will help us to understand. There are 10 tokens for breaking up I love mountains. What happens when we applied GPT-2 tokenizer? You can see that only there 1, 2, 3. Obviously, because GPT-2 tokenizer is trained on a very large amount of text, so and there are no rules for that. Like here we are trying to apply like two adjacent pairs, and basically is focused on dual characters. In GPT-2 it doesn't happen that, so we are a lot behind that. If we try and optimize and we get to the GPT-2 tokenizer level, maybe we can, but here it's just for educational purpose. You can see that there's a lot of difference, and we have got like only 3 tokens here: I, love, and mountains. Now, in the previous video, I have talked about rare words handling, right? That's what subword tokenizer like BPE are designed to do. Let's look at a very rare word called football leashish, right? You can see it is broken up into 1, 2. Let's measure the length here. 9, right? Whereas in case of GPT-2 tokenizer, you can see that it's just 2, right? Because it's optimized and it's very well defined, so you got like just 2 tokens. But our goal was here to understand the BPE tokenizer through like implementation, and we have done that here. If you find this video useful, please like and subscribe. Thank you.